Correction for homework number 3. We have a water tank with specific dimension. There is a square gate with a hinge located at point O. The bottom side of the square gate rests on a drain pipe of diameter 1 foot. The center line of the diameter is located at 3 feet horizontally from the head, from the hinge. The width of my tank is 4 feet, and with all those dimensions, the question is, what is the height h of water above the bottom plate at which the gate actually opens? So we want to find h. We want to find h. In your exam you will write find h for gate to open. So this is a problem of hydrostatics. We are going to use the formula derived in class, in particular force on a vertical wall, 1/2 rho g h square times the width. Well, the first thing is really to define our coordinate system and everything else. So this is our gate. I am conveniently going to place the origin of my coordinate system at the hinge. And so I have x, or vector I. Here I have vector j, sorry, not j. Let's be consistent with k. With the hydrostatic, so that's the z coordinate. And then the freehand rule tells me that y or j has to be oriented inside the board. Alright, so this is our gate. This is our system of, this is our control volume in a way. The control volume is the gate, so CV, that's gate. So let's consider first the vertical plate. The vertical plate is subjected to a linear pressure distribution. Here we're going to solve everything at gauge pressure. Why? Because the top surface is at gauge pressure and the drain is, the top surface is at atmospheric pressure and the drain is at atmospheric pressure as well. So with gauge pressure we have the total force is Fp1, which is equal to rho g h square over 2 W minus I. And the center of pressure is h over 3 from point O. Okay? What is the action of that force? Well, it's kind of obvious. Intuitively, you'll see right away that this force really wants to open the gate, and basically the gate pivot toward the left. Now, let's look at the the horizontal plate. Oops, I am too close to some button here, horizontal plate, so I apologize for that. Notice that there is no dimension of the plate whatsoever. Why? Because the plate, according to the statement of the frame, is thin, meaning that the pressure on top of the plate and the pressure at the bottom of the plate are the same. If that's the case, any point of that plate that sees the water on its top and in its bottom is basically fully equilibrated as far as the force of pressure is concerned. So really, the only place where we have any difference is where the drain is located. So let me draw my drain here. So this is our situation, and if I want to draw the distribution of pressure, I have that constant distribution of pressure on top, and I have the same constant distribution of pressure at the bottom, and P at the top is equal to rho GH, and P at the bottom is equal also to rho GH. So the net force of pressure is really FP2, and it's only over the surface area of the drain, because on the other side we have zero gauge pressure, or we have atmospheric pressure. So FPG is equal to rho GH, so that's the pressure, times the surface area, pi d square over 4 minus k. And remember that this force is located at a distance that we're going to call L, equal 3 feet from the hinge O. Alright, so how are we solving the problem? We are stating that right at the moment when the gate opens, when at the last limit of the equilibrium, the moment of the force of pressure on the vertical wall is equal to the moment of the force of pressure on the horizontal wall. So that's the moment of FP1 about O plus the moment of FP2 about O is equal to 0. So I'm just trying to figure out my final rule. Again, let's draw quickly sketch. We have FP1 here, and we have FP2. Obviously, FP1 wants to create a moment this way, whereas FP2 create a moment the other way. Okay. So according to our rule, we have the first one is going to be a minus, but the bottom line is that they're both opposite in direction. So we can solve, so the moment of FP1 about O is equal to H over 3K cross product rho GH square, sorry, jumping ahead, over 2 times W, which is the width, minus I. And so this, so K minus I, it's going to give us a minus rho g h cube over 6 W J. Moment of FP2 about O is equal to L, well, I'm going to write it rho g h L pi d square over 4 j. So the sum is equal to 0. I can just say that one is equal to the other in magnitude. I can simplify also by, well, let's just write everything. Rho g h cube over 6w is equal to rho g L HL, sorry, pi d square over 4. Simplify by rho, by g, by 1h, and I have h square is equal to 2 d square pi L, 6 pi L, sorry, over 4W. So d square 2 pi L over, no, sorry, 3 pi L over 2W. So h is equal to d square root of 3 pi. So now L and W are the same unit, so it doesn't really matter with JR. One is 3 divided by, so 3 feet, and the other one is 4 feet, so 2 times 4. So that's D is equal to 9 pi, square root of 9 pi over 8. And when this is all said and done, I find that H is equal to 57 centimeters. And this is it.